Hello and welcome to our introductory video talking about our PNC force sensing material and our PNC force sensor kit, explaining the advantages and the performance of this material and our sensor kit. After this video, you will understand the composition of our force sensors, the range, and some of the applications that can be produced with some of our force sensing material. For the basis of our technology, we take our polymer nanocomposite. That's where we get the PNC from. Polymer nanocomposite is a medical grade silicone base that we have made electrically conductive by integrating nanoparticles into this material, which is making it electrically conductive, and it is not coated. It is 100% conductive in the X, Y, and Z axes. Which means whenever a force sensor material is cut out of this material, it can then be placed onto electrodes, and the change in electrode conductivity can then be measured, which I can exemplify very simply by showing you our LED ring. So here we are measuring just the resistance of the material using an Arduino Nano and a voltage divider. And so when the material is pressed, electrical conductivity changes, and we can measure that change in conductivity and extrapolate the force that is being exerted on this material. How a force sensor itself would be constructed, as is found in our force sensor kit, is this would be the material that we cut out of a mat, and then that is then placed onto electrodes to make a passive force sensor element. Like in our force sensor kit, what you can see is we have an extension of this principle to we are not measuring just the resistance, but we are measuring also the capacity of our material with our impedance electronics. And then in the kit, there are 5 sensors, an LED ring, and we will be using this technology as the basis for the demonstrations today. If you would like to learn more about this kit, we have an unboxing video that will be linked at the end of this video. So let's go ahead and take out one of our force sensor electronics and go ahead and connect it to our computer using an open source serial plot software. So we can exemplify the sensitivity and the range of forces that can be measured by using this. So we have now connected the computer to where we will be able to update, refresh, and hopefully find it. There it is. And then we'll open it. And so with this, I have the force sensor connected to where I press on it. You can see the raw data that is being put out by the electronics. In our force sensor kit, we say that we can measure 1 gram up to 15 kilos when using an extension cable. And so I'm going to show some of that performance of the sensor by using some standard weights. But right now we're going to see what this can be used by measuring the weight of a coffee bean. Now this coffee bean weighs 120 milligrams, which is far below the rated range of 1 gram was in our data sheet. But depending on the configuration, we guarantee 1 gram up to 15 kilos. If I place this coffee bean on the sensor, you can see the rise in sensor performance by the weight of the coffee bean. And so that is showing a very high sensitivity of our material just with the small weight of a coffee bean. Ideally, the surface of the sensor will be completely compressed, so not just one part of it, as I'm doing here, but more distributed, like a cap, for example. So I'm putting a piece of plastic on top of it so that we can evenly distribute the force along the entire surface of the sensor. And to demonstrate the sensitivity, I have got some other weights here to be able to show you what is going on. So here I have a weight that is 1 gram. If I put it onto the sensor, you can see that the sensor reacts very well to 1 gram. Let's go ahead and put 2 grams on top of that, so we have a total of 3 grams. And then we'll take another 5 gram weight, which will be a total of 8 grams. And here you can see the sensor performance keeps going up with a very high sensitivity. Let's take all of these off and put down a 10 gram weight, which is close to what we had with the 8 grams. And then we'll put down a 20 gram weight. And then let's jump up to 50 grams. And you can see the change, the increase in the material response. And then here is a total of 100 grams that is then being placed onto the material. Now the response of the sensor is very sensitive in the low force ranges. Being able to measure a coffee bean, for example, or 2 or 3, we can measure individual grams. But as the force increases, the resolution decreases, so unfortunately if I put a coffee bean onto this 100 gram, we barely see a change in the response. Which means for forces in the low force range, we have a very high sensitivity. But we are also able to measure very high forces with our material, which is why I have another demonstrator here, being able to show the high force range. So let me put all this back so I have some space. Now put all these back, there we go, back in their place. And then let's switch over to the other demonstrator that I have. The other demonstrator is this pedal here. And it's the same configuration as we're using here to measure the coffee beans, but it is put into a more robust housing. Pull this ahead so we can see that in the camera. And with this construction, we have a metal construction, which is very robust. And we use this for trade fairs to exemplify the very high force range that we have. Underneath, we have a force distribution puck, and then this is the force sensor that you can see at the bottom. And once I put that underneath there, we have the weight of this lever, but we can also do a whole lot more, exemplifying the total weight capability of the force sensor. So let me go grab some weights over here. We say in our data sheet that we can measure up to 15 kilos without a cable. And what I have just put on here is a 10 kilo weight. And you can see the sensor increases even further. I'm going to grab another one of those. And then we can put a total of 20 kilos, on top of the sensor. And then here you can see, blocking it, the sensor response in the background, being able to measure the additional weight. But we have already reached the maximum of this construction. So for very high load forces, we do have a very broad range. Of being able to measure individual coffee beans in the lower region, but also being able to measure high loads in itself with the same sensor. And so, like I said, all of these components that I've shown today are part of our force sensor kit, which is using our polymer nanocomposite material as the base. And if you are interested in hearing or learning more about a force sensor kit, then I invite you to check out our unboxing video and also check out some of the other videos we have exemplifying the robustness of the material, overload resistance, and in the future, more videos will come.